Okay, let's go, beta. Let me put up the presentation.
This great circle assignment, which has 19 questions, if
Hmm.
we do that, it covers all types of great circles.
After doing the assignment, beta, please go into past papers. Okay, try practicing questions from there. You will yourself get the answer.
Okay, sir.
Okay.
सर ये जो चार्टवर्क में हमने कॉग्ड हेड किया था और ये टेरेस्ट्रियल वाले में बहुत फर्क है ऐसा बोल रहे थे सर, तो
Yeah.
क्या
This is
मार्क्स हैं?
different, beta. Totally different. So you have seen the chart work one. Now forget about that and look at the celestial navigation. Okay. Let's now move on to the topic of resolution of a cogged hat. So first of all, let us see what does a cogged hat mean. Whenever three or more bearings are taken from a ship and they do not intersect at a single point, instead they form a triangle. This triangle is known as a cogged hat. Now usually when we fix the position of the ship, we take two observations, two position lines, and wherever those position lines intersect, that is the position of the ship. Now in case three observations are taken and there are three position lines, and when we plot them on the chart, and if we observe that these three position lines do not intersect at a single point, but instead they make a triangle, then that triangle is known as a cogged hat. Now the doubt which arises in our mind is, what is the reason why these three PLs are not intersecting at a single point? The reason for the formation of a cogged hat, or the reason why PLs are not intersecting at a single point, is because of some error. There is some error in one or all of the PLs because of which they are not intersecting at a single point. If there was no error, all the three PLs would have intersected at a single point only. Now there are two possibilities of formation of a cogged hat. Cogged hat can be formed in case of terrestrial bearings. Terrestrial bearings means bearing of land-based object. Say for example, you have three lighthouses and you take the bearing of these three lighthouses, and when you plot it on the chart, it does not intersect at a single point and makes a triangle. Now this kind of triangle or cogged hat, which is formed because of land-based object bearings or position line obtained from land-based object, is known as a terrestrial cogged hat. Let us first see how do we resolve a terrestrial cogged hat. Now the very important and the foremost thing which should be clear in our mind is that if unknown errors of different signs or magnitudes are present on the different bearings, it cannot be resolved. That means if the error present in the position line is not a similar error in all the three observations, or in other words, you can say one of the observation is having an error, the other two are accurate, or two observations are having an error, but the third one is accurate. In this case, the error is not same on all the three bearings. If the error is not same, the cogged hat cannot be resolved. The only possibility where cogged hat can be resolved is when the error in all the three position lines in all the three bearings is same. Now, if we ascertain that the error is the same, how the same error can be generated? It can be generated because of a compass error. You were taking bearings with a gyro compass and you did not apply the compass error, or you did not know the compass error. So that's why the cocked hat was formed. Now all the three PLs are having a similar kind of error. Or you have taken an error using a magnetic compass. You did not know the accurate deviation of the ship. So you were not able to get the accurate compass error, and all the three PLs were having a similar error. This kind of cocked hat, where the error is exactly the same on all the three position lines, can be resolved. Now, how do we resolve a terrestrial cocked hat? A terrestrial cocked hat is resolved using the horizontal angle method or horizontal sextant angle method. Now, horizontal angle method is used in chart work, and in this method, if we have obtained two bearings from two objects, we use those two bearings to obtain the horizontal angle between the object, and using that horizontal angle, we can obtain a position circle. So using two objects, we obtain one position circle, and using the third object with one of these two gives us another horizontal angle and another position circle. Wherever these two position circles intersect, that gives us the fix of the ship, and once the fix is obtained, we can obtain the true bearing of all the three objects, and comparing them with the compass bearings, we can also obtain the compass error. So the position of the ship is fixed and the compass error is obtained using the horizontal angle method. Horizontal angle method is covered in chart work. This was how terrestrial cocked hat is resolved. Let's now move on to the resolution of a celestial cocked hat. A celestial cocked hat means that we have taken three observations using celestial objects and we have obtained three position lines. When we plot these three position lines on the chart, they do not intersect at a single point and instead make a triangle. This triangle is known as a celestial cocked hat. Now, when we are resolving a celestial cocked hat, the first important point to be clear in our mind is the same one, and that is that in case the error in the three position lines is different, then it cannot be resolved. The foremost condition for resolution of a cocked hat is that the error in the three position lines should be similar, of same sign and same magnitude. If the error in all the three PLs is similar, then the cocked hat can be resolved. Now, for resolving the cocked hat, the first thing which we need to check is that whether the three bearings are contained within 180 degrees or not. Now, what does this step mean? Let me explain to you. Now, how do we find out in a particular question whether the bearings are within 180 degrees or not? We can easily understand it using a simple example. Let's assume that we have a DR position in this particular location and we have obtained three celestial observations. Let's assume that the first observation was taken using the red colored star. It is identified as star 1 and is having a azimuth of 050 degrees. Let's mark the azimuth in the diagram. You can see the azimuth coming up. Let's assume that the second sight was taken using this blue color star, star number 2, having a azimuth of 358 degrees. So you can see the azimuth of the second star also. Let's assume the third PL was obtained using the green color star marked as star number 3 on an azimuth of 330. We are just assuming some values to understand the concept of how to identify whether bearings are within 180 or not. Now, once you have made this simple diagram, having the DR position and having the three celestial bodies and their azimuth, now you try to draw a straight line passing from the DR position so that all the three objects should come on one side of it. I repeat again, we try drawing a straight line which is passing from the DR position in such a way so that all the three objects come on one side of that line. If it is possible to draw that kind of a line, the bearings are said to be within 180 degrees. If it is not possible to draw such a line, the bearings are said to be not within 180 degrees, or you can also convey the bearings are stretching outside 180 degrees. Now let's try to see in our scenario, in our example, whether we can draw the line or not. Now in this case, you can easily draw a line lying in the east-west direction, east-west orientation. You can see this maroon line coming up on the screen. Now this line is passing from the DR position and all the three stars are on one side of that line. So since all of them are falling on one side of the line and it is possible, these bearings are within 180 degrees. So in this particular case, the bearings lie within 180 degrees.
This straight line we will always draw on the latitude.
I will show you the... Go ahead, Bida. Go ahead.
Yes, sir. This the straight line which you just now draw, is it like how we will draw? Sir? I mean, on what basis?
Beta, any straight line passing through the DR position.
Okay, sir.
Anyone. It not necessary in the east-west direction. You can draw it in any direction. So it should be drawn in such a way that all three stars come on one side of it. If it is possible to do that, bearings are within 180.
Okay, sir. Let's say if I have drawn the line from star one, I have crossed it on the opposite, then it still comes 180 between all
Yes,
three.
that's correct, Beta. It will still come.
Okay, sir.
The second scenario where the bearings are not within 180 degrees also in the next slide. Let's now try to see an example where the bearings do not lie within 180 degrees or they are stretching outside 180 degrees. We follow exactly the same procedure. We make a small diagram, rough diagram. First we plot the DR position. You can see the DR position coming up on the screen. Then we plot the three celestial bodies and their azimuth. We have the red star, which is star number 1 at an azimuth of 050. You can see the azimuth coming up on the screen. The second star which we used in this example is the blue colored star, star number 2 on an azimuth of 178 degrees. Let's mark the azimuth of the star. And the third star which we use for this particular example is the green colored star, marked as star number 3 on an azimuth of 330 degrees. You can see the azimuth of all the three stars coming up in the diagram. Now if you try to draw a straight line passing from the DR position, it is not possible to draw a line in such a way that all these three objects, all these three stars, star 1, star 2 and star 3, they lie on one side of the line. It is not possible to do that. Whichever line you draw from the DR position, you will see some of the stars will lie on one side of it and some of the star will lie on the other side of it. So in this particular case, it is not possible to draw a straight line passing from the DR position in such a way that all the three objects come on one side of it. So that tells us the bearings in this case are not contained within 180 degrees. They stretch out of 180 degrees. They are not contained within 180 degrees. Clear, beta? Any doubts?
Clear, sir.
Sir, on the line is also okay, na, sir? If star
Yeah,
3 and
on the
star.
line is also okay. You can extend any one of the line, and if the remaining two stars are on one side of it, the bearings are within 180.
I mean, if both the stars are 180 away and one is on the center, still it is okay, na, sir?
Okay, now that's not possible, beta. In these type of questions, you cannot have two stars in reciprocal directions. Because if you have two stars in reciprocal directions, a triangle will not be formed. Okay, the PLs will be running parallel to each other. So a cocked hat question cannot be made with that.
Okay, sir.
Okay.
Okay, sir.
Okay, all right. So you can now identify whether the bearings are within 180 or outside 180.
आइडेंटिफाई कैसे करें कि विदिन द 180 डिग्री है सर?
बेटा ये पिछली दो स्लाइड्स में हमने क्या किया है? आइडेंटिफाई तो किया है. Ask, did you understand, beta?
No, sir, no, sir. Just that's why I'm asking, sir.
Okay, so now tell me what is your doubt, beta?
Doubts identify this within the 180 degrees, sir. That's why.
Okay, so you want to identify whether the bearings are within 180 or outside 180. You have
Yes,
doubt
sir.
in both of them, within 180 also, outside 180 also?
No, sir. First, I know if I know the one within the 180 degree, automatic will be I know, sir, 180 degree more than.
Right. Now for within 180 beta, if you can draw a line from the DR in such a
Yes.
way that all the three stars come on one side of it, like you see in this situation right now. If you get this kind of a scenario, the bearings are within 180. So can you do this? Is it getting clear, beta, or still doubt?
Still doubt, sir.
Still doubt. Okay. So what you do, beta, I will take you to the whiteboard. You write down three bearings of your choice. Okay. Any three bearings. Okay. जिसमें भी आपको डाउट आता है, any three bearings, just note it down. We will try to test them whether they are within 180 or outside 180. Okay.
Yes, sir.
Let's go. Okay, so let's plot the bearings here and see what happens. First, I will make north, south, east, west, the four directions. Okay, now you tell me, beta, the three bearings of your choice. Go ahead, beta.
330, sir.
330. Very good. Let's draw 330. This is 330. So I have drawn 330. Bearing 1. Great. Next one.
050, sir. Same as.
050. So here is 050, beta. Next one.
335, sir. 358.
358. Okay.
358, sir.
358. Okay, so let's mark 358 also. 358 would be somewhere here. Right, beta?
Yes,
This
sir.
is 358. So we have the three bearings now. Now tell me, is it possible to draw a line passing from this position, the DR position, so that all three of them come on one side of it?
Yes, sir.
Very much possible, beta. You can draw a straight line like this. And if I draw it in this way, you see all three of them. They come
Within
on
the
one side of this line. So this tells me bearings are within 180.
yes, sir. Within the one.
Okay, these are
Yes, sir.
within 180. Now clear?
Yes, sir. Clear, sir. This is clear.
Okay. Now let me give you another example. If instead of 358, the third bearing was not 358, but something else. If the third bearing was, let us say, 230, it will not be 230. Let's call it 200. It was 200. So third bearing is 200. Okay. Let me erase the unnecessary lines. 358 is cancelled now. We do not have 358. These are the three bearings now. This is 200. Now you tell me, beta, is it possible to draw a straight line so that all three of them come on one side of it? All three of the stars?
No, sir. Because they are out of 180 degrees, sir. Yes.
That's correct. So there is no way you can draw a line that all the three stars come on one side. Whichever line you draw, one star will be on one side, another will be on the other side. So bearings are not within 180, they are stretching outside 180.
Yes, sir.
Clear?
Yes, clear, sir. Now clear.
Very good.
Thank you, sir.
Sir, if the third bearing is 230,
Okay. Third bearing is 230. Okay. If it is 230, beta, they are going to be reciprocal. Okay. यहाँ आ जाएगी ये. It will be totally reciprocal of 050. Okay. Now that's not possible because with this the cogged hat will not be formed. What will happen in this case is one PL will be running like this, another PL will be running like this. They will be both parallel to each other and they will never meet. So a cogged hat will not be formed. So this type of question cannot be made.
understood, sir. Understood. Thank you.
Okay. Okay. Great. Let's go back to the cogged hat now. Now, once we have identified whether the bearings are contained within 180 degrees or they are stretching outside 180 degrees, we can now start the procedure to resolve the cogged hat. So we are now going to see the first example in which the bearings are not contained within 180 degrees. So in our plot, first of all, we mark the DR position. There are three observations. And for this example, let us assume that all the three observations were taken using the intercept method. So you can see the first celestial body, the first star, red color star coming up on the screen. This was used to obtain our first PL. This is star number 1. Let's mark off the azimuth of star number 1. You see the azimuth coming up. Now let's assume the intercept was towards. If the intercept is towards, then from the DR position, we go towards the star up to a distance equal to the intercept, and the point where we reach is the ITP, intercept terminal point. So you can see the ITP point coming up on the screen. The position line passes from the ITP and is perpendicular to the azimuth of the body. So we can now see the position line of the red star coming up on the screen. The first position line is plotted. Let's assume that the second star which we used was the blue star in this location. This is star number 2. Let's mark the azimuth of the star. And let's assume that in this case also the intercept was towards. So from the DR position, we go towards the star equal to a distance which is equal to the intercept obtained, and we reach up to the ITP, intercept terminal point. You can see the ITP coming up. The position line will be passing from the ITP and will be perpendicular to the azimuth of the star. So let's mark the PL. You can see the number 2 PL, the blue color PL coming up. It is passing from the ITP and it is perpendicular to the azimuth of the star. This is position line number 2. Now let's mark the third celestial body. You can see the green star coming up. Let's mark the azimuth of the star. Now this star site was also worked out using the intercept method, and let's assume the intercept was towards in this case too. So from the DR position, I go a distance equal to the intercept towards the star, and I reach up to the ITP intercept terminal point. ITP point is marked, and the PL passes through the ITP.
Sir, your
and
voice is
perpendicular
echoing, sir.
to the azimuth of the body.
Echo हो रहा है sir.
Sir, voice is echoing. Voice echoing.
I'm just logging out and logging in again, beta.
Okay sir.
The 3 position lines on the screen now: red color PL, blue color PL, and the green color PL, not intersecting at a single point but instead making a triangle. So this is a cogged hat. Now if you look carefully, the bearings of all the 3 stars are not contained within 180 degrees, because it is not possible to draw a line from the DR in such a way that all 3 of them come on one side of it. It is not possible to do that. The bearings are not contained within 180 degrees. Now how do we resolve this cogged hat? Now for resolution of the cogged hat, you see this triangle which is being formed has 3 vertices. Let's name the topmost vertex as A.
Excuse me, sir. Sir, can you tell me why it is not within 180? Because
Okay, beta, try drawing a line from the DR position in such a way that all the 3 stars come on one side of it. Can you do that?
yes, sir. Understood, sir. Sorry. Okay. Yes, sir.
Okay.
Okay.
Okay. Now this angle of the triangle which is being made, represented by this blue color arc, we have to bisect this angle, or we have to draw the angle bisector of this particular angle. The second vertex where the red and blue lines intersect is marked as Bravo, and the third vertex is marked as Charlie. So as mentioned earlier, we now have to draw the angle bisector. So we draw the angle bisector of angle A. You can see the dotted line. It is the angle bisector of angle A. It divides angle A into two equal parts. The dotted line shows the angle bisector.
I mean,
Similarly, we draw the angle bisector for angle B. You can see the angle bisector for angle B also coming up. And likewise, you draw the angle bisector of angle C. You can now see the angle bisector of angle C also coming up. All these three angle bisectors should intersect at a single point. This is a geometry principle that all the three angle bisectors of a triangle intersect at a single point. And this point where the angle bisectors intersect is the fix of the ship. So you can see the fix symbol coming up. We have a circle and also signified as fix. So this is how we resolve the cocked hat when the bearings are not contained within 180 degrees. So very simple method. Draw the three position lines, have the cocked hat or a triangle on your plot, draw the angle bisector of all the three angles of the triangle, and wherever these intersect, that point is the fix of the ship.
So whatever angle for A which I bisected should be the same value I should use for B and C, right?
I didn't get you, beta. Which value?
Let's say I have bisected the angle A. I got the one line, right?
Right.
So the same value I should be using for B and C, right?
Value for what, beta?
We are bisecting angle A, right? First we will take some value, we'll cross from red line and green line and...
No, don't take any value, beta. Let's assume that this angle A is 60 degrees. You take a D, take a protractor, measure this angle. Let's say this angle is 60 degrees. Divide that by 2, right? It becomes 30. Make a 30-degree angle either with the red PL or with the green PL, any one of them, and you get the angle bisector.
Okay, sir. So likewise, I need to measure for angle B, then divide by 2, whatever is coming, then I bisect.
That's correct, beta. If angle B is 40 degrees, you divide it by 2, half will be 20. Make a 20-degree angle either with the blue PL or with the red PL, you get the angle bisector.
Okay, sir.
Clear, beta? Any more doubts in this?
Sir, I have bisected, let's say for B, I have bisected 20 degree from the red line, and I have bisected 20 degree from the blue line. Then to draw the bisect line, how do we draw, sir?
Beta, when you make an angle of 20 degrees with the red line at point B, you will get a single line. Na? That is what this dotted line or angle bisector is. You have a 360-degree round, beta. You have it.
Yes, sir.
Place it on B. Center it on B. Okay. Keep the red line at its 0. Okay.
Okay.
Keep the red line at its 0 and draw a dotted line in the direction of 340. This is 20 degrees angle then.
Okay, sir. So both the sides, it should be same value.
It will automatically be same, beta. If it is 20, if this angle is 40 degrees and you make an angle of 20 degrees with either of the side, the other one will automatically be 20.
Okay, sir. Okay.
Isn't it?
Okay, sir.
Okay. Any more doubts? Very good, beta. Great. That was the resolution of a cocked hat, bearings not contained within 180. Now let's see the second case. The second case is a little complicated, so pay attention. Let's now move on to the second scenario where the bearings are contained within 180 degrees. Let me show you an example. Let's assume that we have the DR position at this particular location. You can see the DR latitude and longitude coming up on the screen. Let's assume that this was the first star which we used for our site. This is star number 1. The site was worked using intercept and we obtained the intercept towards this body. So let's mark the azimuth of this star. You see the azimuth coming up. The intercept is towards, so from the DR position we go towards the body a distance equal to the intercept, and the point where we reach is the ITP, intercept terminal point. We know that the position line will pass from the ITP and it will be perpendicular to the azimuth of the body. So you can see the first position line coming up on the screen. The red position line is there in our plot. Let's assume the second star which we used for our site was this blue color star, star number 2. And in this case, the intercept which was obtained was away. So let's first mark the azimuth of the star. You see the azimuth coming up. The intercept is away. So from the DR position, we move away from the body a distance equal to the intercept and we reach at the ITP. Once the ITP is there, we can now plot the second PL. You can see the blue color position line number 2 coming up in our plot. Let's assume the third site which we had taken is by using this green color star, star number 3, again worked out with intercept, and the intercept is towards in this case also. So from the DR position we go towards the body a distance equal to the magnitude of the intercept. We reach at the ITP, intercept terminal point. Passing from the ITP is our PL and it is perpendicular to the azimuth. So we have all the 3 position lines now in our plot. Red, blue and green position lines. And these position lines are not intersecting at a single point, but instead making a cocked hat, making a triangle. And we have the cocked hat now in our plot. Now you can easily see in this diagram that the bearing is contained within 180 degree. The bearing stretch of the 3 stars is contained within 180 degrees. How can we check that? Very easy to do. The method was to draw a line from the DR position in such a way that all the 3 celestial bodies fall on one side of that line. And here we can see that if we draw a line in the east-west orientation, passing from the DR position, a line in the east-west orientation, then all these 3 stars, red star, star number 1, blue star, star number 2, and green star, star number 3, will fall on one side of that line. And when that happens, it means that the bearings are contained within 180 degrees. So in this case, the bearings are contained within 180 degrees. Now, whenever we have such a scenario where the bearings are contained within 180 degrees, we will always be able to identify one particular star which lies in between the other 2 stars. Like in this example, we see the red color star, the blue star, and the green star. Now, if you look at the stretch of the bearings, you will be able to understand that the red color star is at one extremity, at one end of the stretch. The green color star is at another end of the stretch, and this blue color star lies in between star number 1 and star number 3. This star is known as the middle star. So I repeat once again, whenever the bearings are contained within 180 degrees, you will be able to identify one particular star which lies in between the other two stars. In this case, in this example which we have taken, the blue color star lies in between the red star and the green color star. So the blue color star is our middle star. Any doubt in identifying the middle star, beta? Now, once the middle star is identified, the next thing which we do is to identify the position line associated with the middle star. So we can see the position line number 2, the blue color position line, is the one which is associated with our middle star. This PL, the blue color PL, position line number 2, is specified as the middle PL, middle position line. Any doubt in middle PL?
Clear, sir.
Now, once we have identified the middle PL, in our case the blue color PL, you will see that this middle PL is involved in making two angles of the triangle. Let us name the vertices of the triangle. This vertex, let's name it as A. The second vertex where the red and blue lines intersect, let's name that as B, Bravo. And the third vertex where blue and green lines intersect, let's name that as Charlie. So we have the three vertices of the triangle, Alpha, Bravo, and Charlie. Now you will be able to see that our middle PL, that is the blue color PL, is involved in making two vertices or two angles of the triangle. These angles are angle Bravo and angle Charlie. Angle alpha is not associated with our middle PL in any way. Angle Bravo and angle Charlie have the middle PL as one of their arms. Can you identify these two angles, beta? Any doubts? So we have to identify the two angles which are connected with our middle position line. In our case, angle Bravo and angle Charlie are connected with the middle PL, which is the blue color PL. Now for these two angles which we have identified, Bravo and Charlie, we have to draw the external angle bisectors. Now what do we mean by external angle bisectors? Let me show you in the diagram. We have identified the middle star, the blue color star, and its associated PL, the blue PL. We have identified the angles which are involved with the middle PL, in our case angle Bravo and angle Charlie. And now we are going to draw the external angle bisectors for these angles. Now this angle which you see in the diagram now, which has come up in the diagram, this is known as the external angle Bravo. It is outside the triangle and it is called as external angle Bravo. Now, in the case where the bearing stretch was greater than 180 degrees, we drew the internal angle bisector. You see, this was the internal angle, and we had drawn the angle bisector of the internal angle which lies inside the triangle. But now in this case, we are going to draw the angle bisector of the external angle bisector. So let's draw the angle bisector now. You see the dotted line coming up as the external angle bisector. This is going to divide this angle into two equal parts. So we have the external angle bisector for angle Bravo in our plot. Now we do the same thing with angle Charlie, angle C. We draw the external angle C. You see the external angle Charlie coming up in the plot, and we draw the angle bisector for this external angle. So you can see the external angle bisector coming up. This also divides angle Charlie, external angle Charlie, into two equal parts. So we have drawn two angle bisectors for Bravo and Charlie. Now for the third vertex, that is alpha, we draw the internal angle bisector as usual. So let's draw the internal angle bisector A. You have the internal angle coming up in the plot, and we now draw its internal angle bisector. You see the dotted line internal angle bisector of A coming up, and you will see that all these three angle bisectors will intersect at a single point. Now this is also a geometry principle. The external angle bisectors of two angle and the internal angle bisector of the third will also intersect at a single point, and this point is our fix in this particular case. So you see the circle coming up, that is the symbol of the fix, and you see it written as the fix in the plot. So this is how we resolve the cocked hat when the bearings are contained within 180 degrees. Important thing to see here is that the fix in this case will always be outside the triangle or outside the cocked hat. In the case, first scenario where the bearings were not contained within 180, the fix was inside the triangle or inside the cocked hat. But in this particular case, where the bearings are contained within 180 degrees, the fix of the ship will be outside the cocked hat or outside the triangle, and it will always be towards the direction of the middle position line. Our middle position line was the blue PL. So you will see the fix will always be on the side outside the triangle towards the side of the middle PL, middle position line. So with this, we complete the resolution of the cocked hat in the scenario when the bearings are contained within 180 degrees. Any doubts, beta?
Sir, why are these two cases? I mean, the fixes are different. One is inside the triangle and one is outside. I mean, logically, how it is solving that for more than 180, it will be inside, and if it is less than 180, then it should be outside the triangle. Then that is the correct fix.
Okay. That is slightly difficult to understand. For that, let me first show you the cocked hat, the index error calculation, beta. Maybe that will help in understanding it. Procedure is clear? You can get the answer?
Yes, sir. Procedure is clear. Only like why in one case the fix is inside the triangle and why in one case the outside one is the correct fix. That
Okay.
question I'm stuck.
For that, just hold on. Let me complete the index error calculation, then I will explain it to you. Though it is not required for solving the questions, but I will explain. Let's first
Thank you,
understand
sir.
the index error.
Thank you, sir.
Okay. चलें आगे. Okay, let's go to the index error calculation now. The index error part is also little tricky. Okay, so pay your attention, beta. ध्यान देना आप, be attentive. हाँ?
Okay, sir.
Let's now move on to the second part of the question. Now, in some of these questions, they may ask you to find the index error of the sextant. Now, we know that this cocked hat is formed because of a error in the observation. We have a similar error in all the three observations. If there was no error, all the three position lines would have intersected at the fix of the ship, but they are not intersecting at a single point, and they are instead making a triangle, and the reason for that triangle as there is some error. Now, if this is caused by an index error and we are required to find the index error of the sextant, how can we obtain it from the cocked hat? Let's see. Now, for finding the index error, we have to select any one of the position lines. Any one of the PL can be picked up. So let's, for our example's sake, we pick up the PL number 1, the red color PL. You can pick up the blue PL, or if you want, you can pick up the green PL. All the three position lines are going to give you the same answer. So for our example's sake, we have picked up the red color position line. Now we have to draw a line passing from the fix which we have obtained in such a way that this line is parallel to our selected PL. So we have to draw a line passing from the fix parallel to the red PL. So we can align our sliding roller or parallel ruler to the red PL, shift it to the fix, and then draw a line parallel to it. You can now see the maroon color PL coming up in the diagram. This is passing from the fix, and this is parallel to our initial PL selected, which is the red PL, PL number 1. Now, if the position line did not have any error at all, if this red color position line obtained from star 1, did not have any error, it would have exactly passed from the fix, and it would be the maroon color PL then. So this maroon color PL is basically the position line without the index error, and the red color PL, which was used in making of the triangle, making of the cocked hat, is the position line with error. So the red position line is the PL with error, and the maroon color position line is the PL without error, or it is the accurate PL. Now the distance between these two position lines, the perpendicular distance between these two position lines, gives us the index error of the sextant. Let me show you in the diagram. You see this maroon color arrow coming up. This shows the perpendicular distance between these two position lines. The red color PL having the error, and the maroon color PL without any error, the accurate PL. This index is what is the index error of the sextant. Any doubts up to here, Peter?
Clear, sir.
Great, very good. Now let's see one more thing. Now, as I told you earlier, this index error can be obtained from any of the three position lines. You may use the blue color PL and follow the same procedure, or you may use the green color PL and follow the same procedure. In all the three cases, you will be getting the same index error. The reason for that is that this point, the fix, is the bisector point, or is the intersection point of all the three angle bisectors. And this intersection point of the three angle bisectors of the triangle, it has a geometrical property that it is equidistant from all the three position lines. So whether you pick up the red PL or the blue PL or the green PL, in all the three cases, you will obtain the same index error. Now this distance between the two PLs gives us the index error. You can measure this distance as per your scale, and the index error magnitude is known. Now we have obtained the magnitude of the index error which was present in the sextant. The second thing now which needs to be calculated or found out is what is the sign of this index error. We are aware that the index error of a sextant can be on the arc or it can be off the arc. So how do we find out whether it was on or off in this particular case? Go ahead, Beta. Any doubts?
So I was asking the same thing, sir. On or off.
Okay. I'll explain.
Thank you, sir.
Now for finding out the sign of the index error, we need to check carefully in the diagram that when we are moving from the PL with error, in our case the red color PL making the triangle is the PL with error. Now from this PL, when you are moving towards the accurate PL or the PL without error, in our case the maroon color PL is the accurate PL. So when you are moving from the error PL to the accurate PL, are you moving towards the body or away from the body? Which body we are talking of here? We are talking of the celestial body which was used to obtain the position line. In our case, the red color PL was obtained using star number 1, the red color star. So we need to now see when we move from the red PL to the maroon PL, are we going away from star 1 or are we going towards star 1? Now you can clearly see that if we move from red PL to maroon PL, wrong PL to accurate PL, we need to move away from the star. So this is the factor which decides whether the index error will be on the arc or off the arc. Now we have seen from our plot that when we are moving from PL with error to the accurate PL, we have to move away from the body, away from the celestial body, in our case the star 1. Now when we are moving away from the celestial body, that means the observer's position should be farther away from the celestial body. The observer's position on the celestial sphere is represented by the zenith of the observer. So this tells us that the zenith of the observer should be farther away from the celestial body. Now this distance between the zenith and the celestial body is given by true zenith distance, in short TZD. So this now tells us if you are moving from PL with error to the accurate PL, the TZD of this particular body should increase. If the TZD increases, your error PL will move to the accurate PL. Now we know that the true zenith distance of a body is equal to 90 minus true altitude. So if TZD has to increase, the true altitude would decrease. The true altitude should be lesser. If the true altitude decreases, 90 minus true altitude would be a greater value, leading to increase in the TZD. So the same thing is mentioned here. We are moving away from the body, the zenith is away from the body, so the true zenith distance should increase. True zenith distance is equal to 90 minus true altitude. So for true zenith distance to increase, the true altitude of the body should be lesser or it should decrease. Now the true altitude can only decrease if we apply a correction to the true altitude, which is negative correction. So if there is a negative correction, the true altitude is going to decrease and the TZD would increase. Now when we apply the index error, we know whenever the index error is on the arc, we put it off or we subtract it. So if we want to have a negative correction, the index error has to be on the arc. So let us now test our logic going backwards. in this particular case, if the index error is on the arc, then the value of the index error would be subtracted. We will apply it as a negative correction, because if the index error is on, it is put off. So if the index error is on the arc, we will have a negative correction to the true altitude. A negative correction to the true altitude would mean that the true altitude value will decrease. If the value of true altitude decreases, that means the value of true zenith distance will increase. And if the true zenith distance increases, the red color PL is going to move away from the star, coming to the maroon color PL. So the PL would become accurate. So our correction in this case, index error correction, is on the arc. So if you are moving away from the body, the index error should be on the arc. Your doubts now, beta?
Sir, this method is index error method also applicable for the triangle contained within 180, sir?
Any triangle, beta, any scenario, this is applicable to all.
Okay, sir.
So then this error PL will always move away from the body only, right? All the cases.
Not always, beta. There can be a scenario where you move towards the body. There can be a scenario that depends upon the question setter. So if it moves towards the body, you know the index error has to be off the arc.
Then the fix has to be outside this PL with error. For a body to move towards the star, the fix has to lie outside the error PL.
Yeah, that's correct. Either the fix has to lie outside, or maybe the azimuth of the stars are something else which makes it possible.
Okay.
Clear, beta? Understood?
Yes, sir. Understood.
Okay. Great, beta. Great. Now, this will complete the question. As far as the solving of the question is concerned, it takes care of the solution beta. You will be able to find the index error as well as its sign. Now, one more thing which I am going to explain to you is, अब आपने डाउट पूछा था why that the fix is getting outside. Okay. Now let's go back to that triangle. अब जो मैं समझाने वाला हूँ, even if you don't understand this, this does not in any way affect the solving of the question. So even if you don't understand what I'm going to explain now, it is perfectly all right. Okay, beta?
Yes, sir.
Okay, okay. So let's go back. Okay, great. Now we go back to the scenario where the fix was outside. So bearing stretch contained within 180 degree and the fix was outside. Now let us assume that the fix was inside. We make the fix inside here. Okay. Now what happens is, if you consider star 1, going from the PL to the fix, you are going away from the body. Right? Agree?
Yes, sir.
Okay. Test it with green star. From the green PL, if you go towards the fix, you are going away from the body. So it works well with the green star also. Right?
Yes,
Now
sir.
try it out with the third PL, the blue PL. If you go from the error PL towards the fix, are you going away from the body or towards the body?
Sir, towards the body.
So that is where the problem lies. Whenever you go from the PL to the fix, for all the three bodies, it has to be the same. Either for all three, you should be moving away, or for all three, you should be moving towards. If this is the
Understood.
fix, you are always moving away from the body in all the cases. That is why the fix is outside.
Got
Clear,
it.
beta?
Yes, yes, I
Okay.
got it.
Now you will not get this fundamental anywhere in any of the books. It is not mentioned there. Okay. So if you have
Thank you,
understood,
sir.
it's a great concept, a great fundamental. And if somebody tries to push you in orals or something, now, and if you explain this to him, he will certainly be very happy with you. Very good,
Thank you,
beta.
sir.
Great.
Sir,
So go
one
ahead.
question. Sir, when the fix is outside, when the stars are more than 180 degrees apart, then in that case, how will you find out, sir, this index error, sir? Will able to?
You mean to say the case which is exactly on display right now?
Yes, sir. Yes, sir.
Okay, beta. Let's do it. Pick up a PL of your choice. Red, green, blue.
Red, sir.
Red PL. We have picked up the red PL. I will follow exactly the same procedure. I will draw a line parallel to the red PL passing from the fix. So let me do that. You can now see a line parallel to the red PL passing from the fix, right, beta?
Yes, sir.
Find the distance between these two, that is between the red line and the new line which you have drawn. This is the magnitude of the index error.
Okay. Same case. Okay.
Exactly. And when you are going from wrong PL to right PL, you are going away from the body. The body is star 1. If you are going away from the body, it has to be on the arc.
Oh, okay, sir. Okay, understood.
Exactly same procedure. You can do it with the blue PL, you can do it with a green PL, you will get exactly the same answer in all three. Okay. Reason for that is, let me explain you a one little more concept. This point which we have found out, beta, this point basically, if you pick up your compass, place it on the fix, open it up equal to any of the PL, let us say green PL. I draw a perpendicular to green PL. I keep my compass centered at the fix, radius equal to the green PL, and you draw a circle. That circle is going to touch all the three PLs like this. This is how the circle will be. And this fix is basically equidistant from all the three lines. Okay. So this is how we get the index error and the fix.
Yes,
अगर
sir.
ये
Understood.
अगर ये नहीं भी समझ में आया तो it is perfectly all right. Just forget about it. Nobody will ask you this deep.
Yes, sir. And sir, just to clarify, just to distinguish between the terrestrial and the celestial cocked hat, just correct me if I'm wrong. In the terrestrial one, we were just bisecting the lines, position lines. Correct, sir?
Right, beta?
Okay, okay. Thank.
Right. There you bisect the lines. Here you bisect the angles.
Okay, sir. Thank you.
Okay. Great, beta. Understood?
Yes, sir.
So can we close this out?
You have any worked example for this method, sir? Cockhead.
Okay.
Can
I'll
you-
give you, beta. I'll give you one.
Okay, sir.
I
Please
will be
post.
sending you assignment. In the assignment, there will be one question on cocked hat also. So you'll be able to practice.
Okay, sir.
Okay, great. So very important concepts covered today. So good. And I will send you the assignment today by in some time. I should be able to send it to you. So work on that assignment. And next lecture, we are going to go into the PZX triangle and the rational horizon diagram. Okay.
Okay, sir. Sir,
Okay,
matlab,
beta.
question number 5 and question number 6 is done.
That's done. Number 5 and 6 is done. We are moving to part C, 7, 8, and 9.
Right, sir.
Okay. Great, beta. That's all for today, and I'll see you in the next class.